and I did different levels of grading based on that. So, okay, so the next topic, and we'll keep going with this. I think we have enough time to make it through an example so that you can do your homework this week. The homework this week is accelerations, rigid body kinematics, accelerations. And then with a little bit moment of inertia stuff. So moment of inertia stuff, it's the same, like we talked about this last time, it's the same kind of topic and equations and stuff that we use. It's just there's two different things. You're learning about that in mechanics and materials right now. That I you're solving for is the resistance to bending. It has units of dimensions cubed, right? BH cubed, four dimensions to the fourth, but it's all dimensions, right? Inches squared or meters, or sorry, inches to the fourth or meters to the fourth. That's the units on that. This is different. So that's the resistance to bending. This is the resistance to rotations. And so it's very similar equations, but different concepts really, okay? And so we talked about this is the equation that this is how you calculate the center of masses, which is how you calculate the center of areas, same type of equations. The mass moment of inertia is just r squared dm versus r squared dA that you use for your area moments of inertia. Right? There's our units. Your units are going to be in mass times distance squared, or dimension squared. So kilograms meters squared, or slug feet squared, or blob inch squared. Okay, but and then we kind of applied it to this slender rod and said, oh look, you can actually calculate these things by integrating and making these assumptions and stuff, but you don't have to do it that way, right? And so the way that we're going to do it is we're going to use these equations, right? So this is page, I think, 605 in your text or somewhere in that vicinity. You can track it down. It's Appendix C, and it has how you're going to calculate the moments of inertia of these things is a matching game, right? You're going to say, oh, this is what my shape looks like. I'm going to look into the back of this thing, and it'll tell me what my moments of inertia are. It's worth looking at this a little bit just to show that there are different axes. We talked about this last time. The moment of inertia about the centroid is going to be less than the moment of inertia about an end, right? So like if you can actually feel that moment of inertia, if I hold my pencil on the end, it's harder to rotate like around the end, versus if I hold it in the middle, it's easier to rotate. And so you should have different values. And so these tables they're usually set up in a way where they have, if I'm taking the moment of inertia about O, okay, or in this case, the x, y, or z axis, it tells us what that is, so that's 1/3 ml squared. Or if I'm doing it about the centroid, which are denoted by those primes right there, and then it'll tell you two different equations. So as we talked about, 1/3 ml squared versus 1/12 ml squared. So it is significantly higher, 4 times higher, rotating at about its end versus around its middle, right? Because the mass is more tightly distributed about the centroid and less and distributed more about there. So you should have different moments of inertia associated with that. Okay, and then the key to this one too is that the moment of inertia about the x or the x prime axis is 0. So when you see slender rods, we assume that they have no resistance about that axis, which compared to the other directions, that is true, right? I mean, all that mass is really tight around that axis. The other one we run into in 2D problems is these disked thin circular plates. And again, in this case, we only do it about its centroids. You can see, depending on if I'm rotating it about the y prime axis, or if I'm rotating it about the z prime axis or the x prime axis, you have different moments of inertia. About the y and the x prime, they should be the same. They are 1/4 mr squared. So you can imagine rotating it about each one of those should be the same. But then rotating it about the z, it's different, right? And so you should have a different one about the z. Thin plates will show up. These things are more into the 3D stuff, these other shapes. So when we get into 3D, we might see some of those. But typically, we're going to have this guy, or the slender rods in 2D. Okay. But then it's very, it's not going to be very fun if we always have just those simple shapes. You want to have some different shapes associated with it, right? And so that's where so you can't just straight up use these equations. You have to use the method of composite bodies. I think this is where people really, I think you guys typically hate moments of inertia. Is that right? They're tedious. They're pain in the butts, right? But we got to do them. We need them. And so method of composite bodies is where you break a body up into multiple components and then you use the parallel axis theorem to combine them. So hopefully by today we'll get through an example here. It's just a necessary evil to get to where we want to go. Okay, so simple shapes tabulated, page 605. Complex shapes break apart and apply the parallel axis theorem to combine them, and that's called the method of composite bodies. The way that this works is here's a blob off to the side, some shape, and it has a centroid, and if I know the moment of inertia about that centroid, can I then get the moment of inertia of this blob over here about this axis instead, right? And that's what you end up doing is you have a bunch of blobs all over the place, and then you determine what you use the parallel axis theorem to get them all about the same axis, and then you add them together is what it is. And so to do that, you use this equation right here. Again, very similar to the equation you use for mass moments of inertia. Whereas I think for area moments of inertia, I think that's just an A is what that is, instead of the mass times the d squared. Okay, so in this case, if I want the moment of inertia about O, so IO is the moment of inertia about O. I about O axis. I center mass, that's the center mass. M O I out of mass. M is the mass. And then D is the parallel distance from center of mass to axis. Oh, actually I put the parallel distance from center of mass to parallel axis. All caps. I didn't mean to do that. That's okay. It works. I really emphasize. That's what that is. Okay. So if I want the center of mass around this axis over here, if I want the moment of inertia about this axis here, I know I have to figure out what the moment of inertia of this blob is about its mass center. That's this. And then I add on to it the mass of this plus d squared, which is the distance between the two parallel axes. Okay? And then that gives me that gives me the mass of this object about that axis. And like I said, the way this works is if I've got different shapes, right, I do the same thing, and I get them all about that, and then I'll just add them up, and then it determines it. So the method for doing this, okay, choose parts, right, divide the object into parts where moment inertia can easily be determined. So that's, you divide it into like those different shapes that we saw on the previous page. Determine the moments of inertia of the parts, right? So you do the MOI of each part, and then and then determine the moments of each thing about the L naught axis, and then you add them all together. Like I said, we're going to do an example here in a second. One key thing to do is key thing to do is, I guess another thing, if you have a hole in something, you use that shape, and then when you do the parallel axis, you put that value in as a negative number. So I think you have a homework problem that has like a plate with a hole in it or two holes in it, and so you do the parallel axis theorem. It's just their moments of inertia end up being negative if there's a hole, and so when you go to add them up, those are negative, and they get subtracted out of the overall moment of inertia. Okay. So an example, right? So if I wanted to determine the moment of inertia of this object about this axis right here, we just determined what it was about its own mass center. That was ml squared over 12. And so I could then transfer it over here and determine it about that axis instead. And so if I say Iy is equal to Iy prime plus md squared. This isn't composite bodies, so this is just an example of the parallel axis theorem. So then Iy is equal to ml squared all over 12 plus mass times the distance squared. That distance is from here to here, which is L over 2 squared. And if you carry out the math there, you get ml squared all over 3. Right? And if you look that up in that table, yeah, that is the answer. Right? The other way you can get there is if you go back to this original integral and carry this out, this exact integral right here, if you carry that out between 0 and L, you get the same thing. You get ML. Right. Just kind of show you both methods there. All right, let's do one that's a little more interesting. We got 15 minutes. Yep, we got it. Oh, went too far. Where this is going to play in, by the way, just why we're doing this, right? What we're going to do next is, we're going to come up with our equations of motion. We're doing F equals ma. We have our equations of motion. We're going to have the forces are equal to mass times acceleration, which we've seen before. And then we need to somehow relate this moment to how much it rotates, what its omega is. How does that moment relate to omega? Or in this case, how does that moment relate to alpha? And so we got to derive that equation. How much this moment causes this to accelerate is going to be dependent upon what I is, what the moment of inertia of this object is. And so we need the moment of inertia of this object so we can get a relationship between that moment and alpha, basically, okay? And which it turns out to be, just to get a little foreshadowing where we're headed. Look at that, several pages of derivation, but it ends up with, almost there, way down here. There's that equation. Moments, sum of the moments is I times alpha, okay? That's what it ends up being. But then what I you use, that's where things get interesting, because if it depends on where you're summing the moments about. But we'll get to that later, just to give you a reason why we're doing all this stuff. Okay, method of composite bodies. Let's do an example with that. Okay, so we have a slender bars of length L. So this is just one object, a T-shaped object. Right? And you could imagine this having a moment on it, right? Maybe, let's say, so I mean, like, maybe this is a pinned connection and this thing is being held and then we release it and then this thing swings down. I think that's one of the first problems we do. We're going to have a mass times gravity going here, right? And so we need to determine what its moment of inertia is because we have to figure out how much it's going to accelerate, okay? And so we're going to do two things. We're going to figure out what the moment of inertia is about this axis over here, and then we're going to determine the moment of inertia about its centroid. You don't need them both. Depending on where you sum your moments, you might need them both, which we'll get to that a little bit later. But we're just going to, for now, we're going to calculate both of those things. And so this is one that screams method of composite bodies, right? Because we have a bar sticking out and a bar right there. So we need to figure out what its moment of inertia are. They're attached to each other. You can't look up this shape in a book, but I can look up this one and this one, okay? So let's do this. So first thing, if you follow those methods, it's kind of divided into different sections. And we'll call that 1 and 2. Object 1 and object 2, right? Two different slender rods. Right? What I like to do, at least when I start teaching this, I like to make a little table. So for part A is what is I about O. Right? And then also in 2D, these are 2D. So all of our rotations are around the Z-axis. So just keep that in mind, right? It's all going to be rotating either around in the K direction, one of those two directions. So really you only care about one moment of inertia. When you do 3D stuff, our moment of inertia actually becomes a 3x3 matrix, that's what you get to look forward to, a 3x3 matrix when we do 3D stuff. But right now it's just going to be one value, and it's going to be the moment of inertia about the axes that's coming out of the board. So your axis is coming out like this, okay? Coming out of the board like that, okay? So I about O, So what I do, like we have multiple bodies. Like I said, when I first start teaching this, that's what I do. I say, well, I'm going to make a mass of I, a DI, I center of mass, I, and then I, ZI equal to I center of mass I, right? Because we're going to do multiple objects here, right? Plus MI DI squared. Right, you will get faster at this, but like when we first see it, I like to do this. So for object 1, its mass, they tell us up above, is just m. Right, they say both of them have a mass of m. The d, though, is the distance between the axes. And so it's the distance between the centroid to the axis that we're dealing with. And so this guy's right here in the middle. And we want that distance over to the axis that we're trying to take it about, right? And so it's that distance. So that's D1 right there. Right? And then, so again, you're like, well, it's the parallel axes. Well, what axes are we talking about? We're talking about this axis coming out here and this axis coming out here. So they're both coming out of the board. It's a parallel distance between those, which is sometimes you'll see in your homework, there's one that gets a little confusing, but you got to think about those axes, the parallel axes that you're looking at are the ones coming out of the board. So that guy's just m. This DI is just L over 2. The center mass of I is ML squared over 12. And then this total mass here, this is going to be ML squared all over 12 plus M times L over 2 squared, which gives me ML squared all over 3. Okay, side note, I could have just done that, right? This was this guy about its end. I can look that one up. That one's in a table, right? The moment, that's actually what I just used as the example up above. Like a slender rod rotating about its end is just ML squared over 3. So if you didn't recognize that, you can just jump right to it and say, well, that one's ML squared over 3. What isn't in the book is, this guy about this axis, which we have to get. That's the next step, right? But like I said, I just showed that as an example. But to be consistent and like stick to our plan, this is what you would do. So now we go to object 2, and you do the same thing. In this case, they both happen to have the same mass, right? But now the DI is the distance between this guy's centroid and the parallel axis, right? And so again, those axes are coming out of the board. And so in this case, that's just going to be L, right? The moment of inertia of that slender rod about its own center of mass is just ML squared over 12. Right? Where this came from was that table, right? That's the moment of inertia of an object, of that object about its own center of mass. And so that's just ML squared over 12, which we derived last time and done before. So then again, the total here is ML squared all over 12 plus mass times now it's L squared. It's not L over 2 squared, but it's L squared. And if you carry this out, you get 13 twelfths ML squared. 1.417 ML squared. Oh, that's when you add them together. That's the real answer there. Okay. So once you get this guy and this guy, they're both about the same axes, and they just add them together. Right? Once they're both about the same axis, then you literally just sum this column down, and then what you get is what the moment of inertia is about its end. So that would be the object's resistance to rotation about its end point. Okay, so that's the first part that I was going to do. The second part says, all right, what is the moment of inertia of that object about its own center of mass? About right there. That's a, okay. Well, it'll be less than this value. It should be less than this value if I do it right. But there's certain cases where you want to do that. It depends on where you sum your moments about. If I sum my moments about my mass center, I would want my I about my mass center. If I sum my moments about my O, I want my moment of inertia about O. But just for the sake of doing this problem, we're going to figure out what the mass center is. One of the problems is right now, I don't know where the mass center is. Right? So this is where we have to use that mass center equation. I got to calculate where the mass center is. So let's, part B, let's do that. Right. Center mass of the whole object. So then those equations for that, it's just a weighted average. X bar is equal to the sum of xi mi divided by the sum of the mi's, the total mass. And what this looks like, when you expand it out, that's where the center of mass of the first bar is at L over 2 times m, plus the center of mass of the other one is L times m, all of that over 2m. And what we get is 3/4 L. So that tells me where my center of mass is, which basically says, as a baseline, I used 0 here as my baseline. So the center of mass is right here. Right, we call that G, I think, right? It's 3/4 L. So we know where that's at now. So then now you do the same thing. You do the method of composite bodies. You make the same type of table, but then now you use the corresponding distances there. So I'm going to cheat because I have a tablet. All right, do the same thing. You look at the two different objects. You look at 1. You look at 2. These are all the same mass. Ooh, distance though now. So now the distances are the distance between this guy here and its center of mass right there. So that's just going to be, this is at 1/2 L, that's at 3/4 L, so the distance in between them is 1/4 L. And then this one over here, this one is at L, and the distance to there, again, that's just going to be 1/4 L in between those two things. So then here, L over 4, M, L over 4. Center of mass of both of those are ML squared all over 12, L squared all over 12. ML squared all over 12 plus M times L over 4 squared. And what you get here is 7/48 ML squared. I'm going to cheat again. The bottom one is the same thing. Being lazy myself this morning. Oop, I wasn't lazy enough. 7/48 ML squared. Right, and then you sum those up. Now they're both about the same place. And so you get 0.292 ML squared. So that's what its moment of inertia is about its center of mass, right? As we said before, that it should be smaller, significantly smaller. So it's tighter around that center of mass, and so it's going to rotate easier about the center of mass versus the other one where it's more distributed away, and so it's going to rotate. Okay. You could also have done this for the second one. You could say or, just to kind of complete our little discussion here, or you could say I about O is equal to center mass plus MD squared. And so you kind of flip this thing around. You could say I center mass is equal to IO minus MD squared. Right? I had already solved for what IO was. And so this could be 1.417 ml squared minus total mass here would be 2m. This is if I'm looking at the whole object, right? I know what the whole object center mass is about here. I mean, moment of inertia is about here. And so then I can kind of figure what it is about its own center of mass using just the parallel axis theorem, which I'm doing right here. I mean, I would probably stick to the plan of just use the method of composite bodies, but if for some reason you notice that, you could do it this way. Right? And so that 3/4 is the distance between right here and here. And so if you do that, you get the same answer. 0.292 ml squared. That's just an or. I don't have to do both. I'm just showing the or. You can do it that way as well. We did it. All right, so Friday's a big day. So now I think you got everything to do your homework. All you're doing is I think 3 or 4 acceleration kinematics problems, right? They're pretty involved. And then just tedious. Then you're doing the sun gear, but with accelerations. And one of them has the wrong answer. You see that on when I posted the homework, one of them has the wrong answer. And so I gave you what I gave you is the right answer, so you should try to match my answer, not the book's answer. And then what we're gonna do is start this, right? Which is F equals MA. All right, have a good day. See you Friday.